Right now, 93 million miles from where you're sitting, a star is burning. It has been burning for 4.6 billion years without stopping, without running out of fuel, without producing a single gram of CO2. And deep inside research labs in South Korea, England, France, and California, a group of scientists are trying to do exactly the same thing, on Earth, in a metal machine the size of a building. What they're attempting is arguably the most ambitious engineering challenge in human history, and they are closer than they have ever been to pulling it off. This is the story of nuclear fusion, what it is, why it matters, why it's been 50 years away for the last 70 years, and why this time it might actually be different. Before we can understand fusion, we have to understand why the world is desperately searching for an alternative to what we already have. Today, the vast majority of the world's energy comes from burning things: coal, gas, oil, fossil fuels. And while we've gotten remarkably good at burning things, we've also gotten remarkably good at ignoring the cost. Carbon emissions, climate change, air pollution that kills 7 million people every year. Now we have renewables. Solar and wind are growing faster than anyone predicted, but they have a problem. They're intermittent. The sun doesn't always shine. The wind doesn't always blow. And storing energy at grid scale is still one of the hardest unsolved problems in engineering. So for decades, physicists have pointed at the sky and said, what if we could do that? What if we could harness the same process that powers the sun, not by capturing its light from 93 million miles away, but by recreating it right here on the surface of our planet? That process is called nuclear fusion, and understanding it starts with something almost impossibly small. At its core, and I mean literally, at the core of the sun, hydrogen atoms are being crushed together by an almost unimaginable amount of gravitational pressure. So much pressure that they fuse. Two hydrogen nuclei become one helium nucleus. And in that collision, a tiny fraction of mass is converted directly into energy, pure energy. Following Einstein's most famous equation, E equals mc squared. The amount of energy released from even a small amount of hydrogen fuel is staggering. 1 kilogram of fusion fuel contains the same energy as 10 million kilograms of coal. This is fundamentally different from nuclear fission, the kind of reaction that powers today's nuclear power plants, where heavy atoms like uranium are split apart. Fission works, but it produces long-lived radioactive waste, and the fuel-enriched uranium is rare and politically complicated. Fusion, on the other hand, uses hydrogen, the most abundant element in the universe. Its isotopes, deuterium and tritium, can be extracted from seawater and lithium. The fuel is effectively limitless. And the waste? Helium, literally the gas you use to fill birthday balloons. If it sounds too good to be true, that's because recreating it on Earth is extraordinarily, almost absurdly difficult. To get hydrogen atoms to fuse on Earth, you can't use gravity the way the sun does. We simply don't have enough of it. Instead, you have to heat the hydrogen to temperatures so extreme that it transforms into a fourth state of matter called plasma. How hot? Try 100 million degrees Celsius. That's not a typo. That is 6 times hotter than the core of the sun itself. At that temperature, you obviously cannot let the plasma touch anything. There is no physical material on Earth that can contain it. So scientists have come up with 2 main approaches. The first, magnetic confinement. Using powerful superconducting magnets arranged in a donut-shaped chamber called a tokamak, the plasma is suspended in mid-air, never touching the walls held in place by magnetic fields so powerful they'd rip metal objects across a room. The second, inertial confinement. Firing hundreds of incredibly precise lasers at a tiny pellet of fuel simultaneously, from all directions, compressing it so fast and so hard that it ignites like a miniature star, living for a fraction of a second. Both approaches work in principle. The problem is energy. For decades, fusion experiments have consumed more energy than they produced. Scientists measure this with a ratio called Q. A Q of 1 means you got out as much energy as you put in break even. Every fusion experiment in history achieved a Q below 1, many far below it. Then there's the tritium problem. While deuterium is abundant, you can extract it from seawater. Its fusion partner, tritium, is extraordinarily rare. There is currently less than 20 kilograms of usable tritium on the entire planet. A commercial fusion economy would need far more. Future reactors will need to breed their own tritium inside the reactor itself, something that has never been done at scale. And there's the neutron problem. When deuterium and tritium fuse, they release high-energy neutrons. Over time, those neutrons bombard the reactor walls, causing structural damage that makes materials brittle and radioactive. Designing materials that can withstand this for years or decades is a materials science challenge that is still being solved. Finally, cost and complexity. The International ITER project, the largest fusion experiment ever built, currently under construction in southern France, has cost an estimated $20 billion and taken 40 years of international collaboration to reach where it is now. It hasn't even started full fusion experiments yet. So, is this just an expensive fantasy? A pipe dream physicists keep chasing? Not anymore. December 5th, 2022, the National Ignition Facility in Livermore, California. Scientists fire 192 lasers at a target about the size of a peppercorn, and for the first time in history, a fusion experiment produces more energy from the fusion reaction than the laser energy delivered to the target. The plasma ignited. It was called fusion ignition, and it sent shockwaves through the scientific community. Now, to be precise, when you count all the energy needed to power those lasers, the experiment still used far more electricity than it produced overall. But scientifically, it crossed a critical threshold. It proved the physics works. It proved that ignition is achievable. And it didn't stop there. By 2023, NIF had repeated the experiment and achieved even higher yields. The numbers were improving fast. Meanwhile, a different kind of fusion revolution was happening outside the national labs. In Silicon Valley, Boston, and beyond, a new generation of fusion startups has raised over $6 billion in private investment, and they're not waiting for billion-dollar government megaprojects. Commonwealth Fusion Systems, spun out of MIT, is betting on a revolutionary new magnet technology using high-temperature superconductors that are dramatically more powerful than anything used before. In 2021, they demonstrated a magnet achieving 20 Tesla, the most powerful superconducting magnet ever built. This could allow for tokamaks that are dramatically smaller and cheaper. Helion Energy, backed by Sam Altman, has a target of achieving net electricity from fusion by 2028, with a commercial power plant online by 2029. Microsoft has already signed a power purchase agreement. This is unprecedented. A major tech company betting real money on fusion power before a working reactor even exists. TE Technologies is pursuing a different approach altogether, using hydrogen and boron fuel, which produces almost no radioactive neutrons at all. If it works, it's the cleanest possible version of fusion energy. The race is no longer theoretical. It's commercial. It's funded. And the finish line is in sight, though nobody knows exactly how far away it is. Will we ever truly make a star on Earth? Not literally, no. A real star is unimaginably vast, held together by the gravity of 1,000,000 Earths. What we're building are machines that mimic one tiny piece of a star's physics. But that tiny piece could change everything. Fusion energy would mean power that is effectively clean, safe, and inexhaustible. It wouldn't solve every problem. We'd still need infrastructure, storage, distribution grids, but it would remove the single biggest constraint on human progress: the fact that energy is finite and dirty. The history of fusion is a story of brilliant people being repeatedly humbled by nature. Every time they thought they had it solved, nature revealed another layer of complexity, another magnetic instability, another engineering limit, another reason to be patient. But patience has also given us 2-0 Tesla magnets, laser ignition, private billion-dollar investments, computational tools that didn't exist a decade ago, and a generation of scientists who grew up knowing that fusion wasn't science fiction, it was an engineering problem waiting to be solved. The stars have been doing this for billions of years. We've been trying for 70, and the gap is closing. Before you click away, 3 quick things. 1, if you made it this far, you clearly love digging into the science that actually matters. So hit subscribe, because this channel is entirely dedicated to these kinds of deep dives, the mysteries and breakthroughs that shape the future. 2, I want to know what you think, down in the comments. Do you believe fusion energy will be commercially available in your lifetime? And which do you think gets there first? The massive government projects like ITER, or the private startups racing to beat them? Drop your take below. I read every single one. Next week, we're covering something that might be even stranger than fusion. We're asking, is there a fundamental limit to how much energy the universe itself can hold? And what happens if we ever hit it? Yeah, we're going there. I'll see you in the next one.